Students, welcome to this solution walkthrough for your digital communications first homework. So let's see the solutions of your first homework, and I will walk you through the steps one by one so that you can know where you lost your marks and what exactly I was looking for. So let's start. The first problem was on this PDF of a random variable, and it is based on the concept of the functions of a random variable. So we had this random variable y, which is a function of the random variable x, and the relationship is ax square plus b, where a is less than 0. So you were asked to determine the PDF of the random variable y in terms of the PDF of the random variable x, which is your f of x. So let's see. So in this problem, basically it had a few details that some of you missed. Most of you got it fully correct. So for example, we have given you a condition that a is less than 0. So if something is given like this, then obviously it means something, and you have to use this in your problem and analyze the different situations of the problem according to the conditions. So to start with, we have this function. So gx equal to x square plus b, which is equal to your y. So your two random variables are related to each other through this functional relationship. So this function has two solutions for x in terms of y, and one is plus of square root over y minus b over a, and the other is minus of the same quantity. So random variables are real valued. So this has to be an important property which has to be applied here. So since the variable x, random variable x, is real valued, so obviously the solutions of the values that it might take should also be real valued. And that being said, since your a is less than 0, so this ratio, to make this ratio positive, y minus b over a, your y minus b also has to be less than 0 or negative, and therefore you must impose the condition that y is less than equal to b, and in only that case this y minus b over a is a positive number, and therefore the square root of that number gives you a real number. So, and of course, since nothing is given for the positivity or negativity of b, we are assuming here that b is positive, and this is the case to make this ratio positive. So with that, we just use this formula. Some of you have derived this formula, which is very good, but I just wanted you to use this formula. If you don't remember, then of course you can derive. In fact, I would encourage you to derive the formula. I don't encourage you to just memorize things for the sake of it. If you understand the concepts of random variable, PDFs and CDFs, then you can derive this formula as well. So then you have the relationship, that is the PDF of y in terms of the PDFs of x. So you just calculate this value. You have already calculated x1 and x2, so your I here goes from 1 to 2, and you calculate dx and use the value of dx at all the values of x, which is x1 and x2 here, and then you just have this expression. So all I wanted is to have you this expression and use this condition, that is a less than 0, and that's it. That would give you full marks on this problems. So now next let's move on to the next problem. In the next problem we had these three waveforms f1, f2, f3, and you were asked to show that these waveforms are orthonormal. So I mean almost all of you got it correct, this part. So all you need to show is that this pairwise integration of fi fj is 0, and then the energy of the signals fi square dt integrated over minus infinity to plus infinity is 1. So in this problem you don't have to go from minus infinity to infinity, because the signals the ranges span from 0 to 4 over the time axis. So all you need to do is to make the integration from 0 to 4, and then depending on the pairwise signals themselves you just divide the intervals accordingly, like how the signals are defined. For your convenience you divide the total interval into several small intervals to actually compute the integration, and you can show that for all pairwise combinations the integrals will be 0. So some of you tried to do it in a different way. So for example, you were trying to show that 3 of them together integrated gives 0. So I just want to have a comment on this. That doesn't work. So you have to show pairwise normality or orthonormality, and then only you can say that all these signals are orthonormal to each other. Doing it 3 at a time doesn't make sense at all. I didn't do the integrals with 3 at a time. Maybe for this problem that might still give you 0, but always that won't be the case. So that is not the condition for orthonormality or orthogonality. So you have to show for pairwise functions and show the integral is 0, and then only you can comment that they are orthonormal. Obviously you have to also show this part. So it's also very straightforward to show that. I have skipped that part in the solution here, but it's easy to show, and therefore with these both conditions shown, these signals are orthonormal. And the next part was again a little tricky. Some of you couldn't solve this part. So you were asked to represent the signal xt, which was given here, in terms of linear combinations of the signals f1, f2 and f3, but you were trying to show, like, so let's say xt can be represented as, let's say, x1 of ft, x2 f2t and x3 f3t. So these are the coefficients of x on the different axes. So x1 is the coefficient of x on the f1 direction, x2 is the coefficient of x on the f2 direction, and x3 is the coefficient of x in f3 directions. So just like you do for a signal, you have phi1 and phi2 as a set of orthonormal basis functions, and you show a signal st equal to s11 S1t equals to S11 of phi1t plus S12 of phi2t. So those S11 and S12 are the coefficients of your signal S1, and they are basically the projections of the signal S1 along the phi1 and phi2 axis. So if you look back into your lecture notes, you will find that we were calculating S11 and S21 by actually integrating the signal S1 with phi1t or with phi2t, to get those projections. So all you need to do is to use that concept here. So you represent the signal xt as a linear combination of f1, f2, f3 like this, and then you calculate the x1, x2 and x3 using these integrals. And if you do so, in this case you will see that x1, x2, x3 are all 0. And therefore, since all of them are 0, you doesn't have a component of xt along f1t, f2t or f3t, or in other words, this signal xt is orthogonal to the signal waveform. So they cannot be represented as a linear combination of f1t, f2t, f3t. So that's all was needed in this question. So some of you got it correctly, but most of you couldn't. And I think after seeing your scripts, I found that you tried to solve this problem in a different way, and that's why you made the mistakes or you got confused. So you were representing xt, let's say, as linear combinations of f1t, f2t, f3t, and you were having these coefficients, like some of you are having these coefficients as a, b and c, or x1, x2, x3, and then you are trying to equate this part at different intervals with the original value of xt, and then trying to solve for these coefficients. So that might work for you, but sometimes for large number of intervals, for example in this case xt had 3 intervals. If you have large number of intervals, you might end up having a large set of equations, and sometimes you might get confused and stuck in solving them. So and for cases like this where all the x1, x2 and x3 are actually 0, you might not be able to solve the set of equations at all. So my advice to you will be to use this process rather than using the linear equation process. So these are the projections of the signal xt. So just integrate the xt with f1t, f2t or whatever is asked in the question, and try to find out the projections by this means. So if you had done this, you will see that all these are 0, and then you would easily get to the solution. So that's it for question 2. Now for question 3, what we had was these two signals S1 and S2, and you were asked to show that these two signals are orthogonal. So you got, most of you again got this correctly. So all you have to show is just do this integral and show the value to be 0, and hence this S1 and S2 are orthogonal. So then you had to show that the two signals have the same energy. Again, that is straightforward. So you have to perform these integrals S1 square t dt and find out the integral to be Es, and then again for S2t you do the same thing and you get the same value. So therefore S1 and S2 have the same energy. Then the part C says that, let's say we have a set of 4 signals, S1t, minus of S1t, S2t and minus of S2t, and let's say they are used for transmission over an HW1 channel. Identify a set of orthonormal basis functions for the signal space. And you are given a hint that you do not have to use the Gram-Schmidt procedure, which indeed is the case, because you have already proved in part A that S1t and S2t are orthogonal, and in part B you have shown that their energy is Es. So they are orthogonal and they have same energy. So you can straight away write the two orthonormal basis functions, phi 1t as S1t divided by square root of the energy of S1t, and phi 2t again as S2t divided by the square root of energy of S2t. So in that way you have normalized versions of these signals, and those are equal to phi 1t and phi 2t. So those are your orthonormal basis functions. So if you see, if you try to show that phi 1t and phi 2t are orthonormal, you have to integrate these two quantities, and you can see that the integral is basically the integral of S1t and S2t divided by Es, and this will be 0. And if you try to calculate the energies of phi 1 and phi 2, you will see that basically the energies are the integral of this whole quantity squared. So S1t square by Es, and the integral of S1t square dt will be Es. So Es divided by Es is 1, same for this, and then you show that phi 1t and phi 2t are orthonormal. So basically, if you apply a little bit of intuition, you don't have to actually use Gram-Schmidt procedure for this. You can straight away write phi 1t and phi 2t, and since the other signals are minus of S1t and minus of S2t, so they are basically 180 degrees phase shifted versions of S1t and S2t. So therefore they can also be represented by the same set of basis functions. So the four signals will look like this. So more or less similar to the QPSK constellation. So you have S1 here and S2 here, and then you have minus of S1 here and minus of S2 here, and that's it. So again, most of you got it right, but most of you didn't. So this was the whole thing. I wanted for part C this specific argument, but then I gave you marks if you had used Gram-Schmidt or just wrote down phi 1t and phi 2t like this without the explanations. I gave you marks on this and didn't penalize you much. So now let's come to problem 4. So in problem 4 again we had three signals S1t, S2t, S3t, which are given in the diagram, and in part A you were asked to show that phi 1t and phi 2t given by these relations are orthonormal. So you got it mostly correct. So all you have to show again for orthonormality is the integral of this product to be 0, which is indeed 0, and the integral of the square of these functions is 1, or in other words the energy of this phi 1t signal and phi 2t signal is 1. So that's the case indeed. So therefore phi 1t and phi 2t are orthonormal. Then in part B you were asked to show that the signal S3, which is this signal, may be expressed as a linear combination of phi 1t and phi 2t. So again, for this part you already okay. So here part B. So many of you just said that by looking into the signal S3t you can say that they are linear combinations of these two signals, which indeed is the case. So for example, S1t is positive here and S2t is exactly the negative of this part here. So these two parts cancels. If you add S1t and S2t, again this part and this part cancels, and all you are left with is a signal whose amplitude is twice square root of E by T, because you are adding this and this, from T by 2 to T, which is the case of S3T. So if you can write it with proper argument, that is fine, but a more straightforward and methodical approach would be just to calculate the projections of S3T along phi 1 and phi 2. So first you calculate S31, and that comes as square root of e, because you have to calculate this integral s3t times phi 1t. So again the concept of projections is coming here as it came for problem 2, and again you calculate s32, so which is again the projection of s3 on phi 2, and you get square root of e, and then you can write s3t as s31 times phi 1t plus s32 times phi 2t, and this excuse me. So that's a pretty straightforward approach, and but if you can argue with logic that S3t is actually the sum of S1t and S2t, and S1t is given in terms of phi 1t as this, and S2t is given in terms of phi 2t as this. So therefore S1t plus S2t is basically square root of e times phi 1t plus square root of e times phi 2t, and therefore your S3t is this, which is also okay. In part C, we were asked to so let's see what was there. So the set of three signals S1t, S2t, S3t are used for transmission over an additive white Gaussian noise channel. Identify a set of orthonormal basis functions for the signal space. Okay, and here also the hint is you do not have to use the Gram-Schmidt procedure, so which indeed is the case. So let's see how is that. So in parts A and B, you have already shown that phi 1t, which is given by S1t divided by square root of e, and phi 2t equals to S2t divided by square root of v. These two functions are orthonormal functions which can represent all three signals S1t, S2t, S3t. So phi 1 is represent S1t because phi 1 is equal to S1t by this quantity. Phi 2 in a similar way can represent S2t, and S3t can be represented with phi 1 and phi 2 as well, you show in part B. So therefore you can represent all three signals S1t, S2t, S3t in terms of phi 1t and phi 2t. So so basically if you have a coordinate system defined by phi 1 and phi 2, so you can have S1 which is only defined by the phi 1 axis, so S1 will be somewhere here, and S2 which is only defined by the phi 2 axis, S2 will be somewhere here, and S3 is defined by both phi 1 and phi 2 given by this expression, so it will be somewhere here. So that's it. So it can represent all three signals. So you don't need Gram-Schmidt procedure always actually, if you can apply a little bit of logic and argument. And the signal space diagram I already drawn here, so in a better way it looks like this, and most of you got it right, so I gave you full marks on this, but this part you again applied Gram-Schmidt, which is okay. I still gave you marks on this part. So that's it. This is the solution, and I walked you through the solution for homework 1, and I hope you have all obtained your grades for this homework, and they are available on Blackboard. So until next time, goodbye and have a good time. Thank you.